And we are live. For the students here, I would like to kind of, I know there's the formal introduction and everything else, but I should say that Ruchi is from a batch where they were highly enthusiastic students, and they pushed the boundaries of what the department could do in terms of making us work hard to ensure that they got whatever they were interested in. I think Ruchi was my student not only for core courses, but also for electives, including microwave physics.
Yeah.
Right. And I was teaching modern physics then, and Ruchi had done a summer internship on gravity waves, and gravity waves had just been discovered. And she came back, and at my request, within, I think, 1 day or 2 days, without a hesitation, came and took a complete class for our students on gravity waves. Without hesitation, without much notice. It was not like I need 1 week, I need 2 weeks. She's like, I know what I did, I'll come and talk to you guys. That was the kind of a person, and those are the benchmarks against which I think the students of the department have to mark themselves and live up to the expectations. I am extremely happy to see Ruchi back here giving a talk, because I know she's a very good speaker. It's a pleasure to have you back, Ruchi.
Thank you.
Nirupama,
Yes,
it's all yours.
Good evening, everyone present here. Hosting for you today is Nirupama, first year IMSc student of physics. I feel extremely delighted to be here on behalf of VINN, Astronomy and Astrophysics Club, Department of Physics, Central University of Tamil Nadu. I cordially welcome all the erudite and elite present here on this virtual platform, and treat yourself high and majestic with this intellectual banquet. We have with us our speaker of the day, Ms. Ruchi Mishra, an alumna of CUTN, now pursuing a PhD at Nicolaus Copernicus Astronomical Center, Warsaw, Poland. We welcome you, ma'am. We are really proud to be with you today and are extremely eager to hear you. And I must mention her research experience from the project, like black hole thermodynamics, black flow and accretion disk, GRRHT simulation of leviating atmosphere, no doubt, certainly frames her as an inspirational figure for young students like us who want to aspire like her. Not just this, her academic achievements like NRTA scholarship, holding a diploma in CERN School of Computing, and her publication on backflow and accretion disk, backflow and simulator MHT accretion disk backflow and resistive MHT simulation, earn her the credit of being a wonderful student of physics for whom we listeners feel proud to be here. She has also attended many conferences and workshops, and her contributions are simply amazing. She has presented her papers at various academic bodies, and her invited talks on her areas of expertise are quite impressive. Computational fluid dynamics for physicists and engineers, simulation of deviating atmosphere, numerical simulation of backflow and accretion disk. These are just to mention a few of her talks. And the list goes on. Without much ado, let us get into the program. I welcome you, Ms. Ruchi Mishra, to take us to the journey to the center of our galaxy.
Oh, thank you so much for the nice introduction, and I am overwhelmed by everything, how ma'am told and how you introduced. So let me share my slide. So can you see the presentation?
Yes, Ruchi, we can.
Okay, so I know that it's a formal thing and all, but I really want to share these pictures with you guys. So I was in CUTN 2018 physics batch. So this is a group picture of our batch. Some of them are missing, but yeah. So I was working with Dr. Ponmurgan, and this is a picture from the research team of Dr. Ponmurgan. Then here there is a picture from a science event that we had, and it was like we were demonstrating this space-time curvature here. And we even made we tried to demonstrate gravitational wave in the fabric of space-time through these things. And then here we have a picture where we are just chilling and eating ice cream like at 12 at night, by the way. Anyways, so let me start my talk with an anecdote. So basically it was 2016, February 11. And by the way, that time Professor Madhurima was teaching us electrodynamics, and we had class probably early morning, if I remember correctly. That day, ma'am came to class and she was like, okay, today we are not going to talk anything about electrodynamics. Today we are just going to talk something else. Then we are like, okay, we don't have to listen to the class. We were happy and excited. Then that was the day she told us about the gravitational wave coming from merging of two black holes. So that was quite exciting for me because I never knew about it that time, and it was really inspiring. I was like completely amazed to know that okay, there are two massive, very massive objects, and they're spiraling towards each other and merging, and the energy is so strong that they're able to create ripples in the fabric of space-time itself. So that was quite amazing. So yes, so this day, 2016 February 11, it was the announcement of the first gravitational wave. So on September 14, 2015, LIGO detected the signal from merging of two black holes, each with around 30 solar mass, and this event happened 1.3 billion years back, and the signal we received was on 2015, and that was quite amazing. So basically the gravitational wave, the frequency is converted into sound wave, and then we can hear how it sounds when two black hole merge. So I don't know if you will able to see the audio, but let me try. Could you hear the audio? Can someone tell?
Yes, yes.
Yes, okay. So that was the sound from colliding black hole. The first one was the same frequency as the gravitational wave. Then the frequency is increased to be better heard by human ears. So that was kind of exciting that we can actually hear two black holes colliding. Now in 2017, there was Nobel Prize in Physics given to these guys for the gravitational wave. And to date, there has been 90 of such waves detected so far. And this is an amazing catalog of the gravitational wave. So with this, you can basically just click in one of the merging event, and you can see what are the initial masses of the black hole, what are the final masses, and some other info of where are they located, how far they are from us, and many more. So this catalog is quite amazing. So let me go back to my presentation. Sorry. Okay, but today we are not going to go into the gravitational wave and things because that's altogether another topic. So today I am going to talk about something exciting, that is supermassive black holes. So supermassive black holes are black holes that has mass millions to billions times the mass of the sun. So we know that we know the definition of black hole, like we have something really compact and nothing can escape its strong gravity. So it has event horizon. So any information that passes through the event horizon, it's basically a one-way traffic and it cannot come back. So we know this thing about black hole, that it sucks everything and all that. But there are different kinds of black hole. There are stellar mass black holes, there are primordial black holes, and there are supermassive black holes. So these are very, very massive black holes. And black holes are the place where the GR effect of Einstein, the general relativistic effects, are very prominent. So this is a best field where we can really understand what is happening in general relativity. And it happens to be that every large galaxy has supermassive black hole at the galactic center. So there are observations that tell us that so all these massive galaxies have a supermassive black hole sitting at the center of the galaxy. So another thing I want to tell is that I hope you can see this text. It's written accretion disk. So basically, when we have a black hole and we have material around the black hole, so the material doesn't just go directly fall into the black hole. Instead, it will be forming a disk around the black hole and slowly getting accreted, getting inside the black hole. So this sort of disk structure happens when there are like dust, gas, particles, and everything in the vicinity of black hole. So that is how the black hole slowly eats the masses around it. And this kind of structure is called accretion disk. So just remember this word because we will be coming back to this thing. So next thing, coming to the supermassive black holes. This is one picture of galaxy MSR 87 or M87. So you can see this blue plasma shooting out from the center of this galaxy. So this is actually a real picture taken by Hubble telescope in visible and infrared. So this plasma is actually jet, and scientists believe that the jet mechanism, the jet launching mechanism, is somehow related to the accretion disk of black hole. But we are not going to discuss more deep into that. Now, scientists now zoom into this very center of the galaxy and they see the image of the first black hole. So this is the center of galaxy M87. I know that this is a very famous image. It came in 2019 and it was all over the internet. And there are a lot of memes, like a lot of them. And this one, basically this picture I took during one of the conferences. So she is one of the scientists in who is behind this black hole image thing. And in one summer school, she was showing this meme page. So this is the picture from there. But among all of them, my personal favorite is this one, what we saw and what South Indians saw. So it does look like a bada. So it was really hilarious that time. So yeah, so there were a lot of memes and it was really famous. So as my my title of the presentation suggests that journey to the center of the galaxy. So I thought to put this video. So this video basically is taken from a press release from the recent image of black hole. So they show here how they are zooming into the center of our galaxy. First, what we are going to see, it's visible. Then they switch to infrared and radio, because we cannot reach that far with the visual. I mean, the light source will be better for radio when we go far. Then let me just play the video. So now we start from Chile, and we are going looking at, okay, sorry, we are looking at the Sagittarius constellation. The video is lagging a bit. Let me just reduce its quality maybe. Sorry. Okay, let me play it again. Just a second. I will reduce the quality. It should work now. Okay. Now we are zooming further into the galactic center. And there we have the first image of the black hole that is present in our galaxy, at the center of our galaxy. So the name of the black hole is, okay, sorry, I have to recast it. Okay. Okay, so the name of the black hole is Sagittarius A star. It is present in the Sagittarius constellation. So here there is some important things about Sagittarius A star from its discovery from 1974. I am not going to go through all of these events. Maybe later you can look at it. So basically the interesting thing here is that there are, the first row took almost 32 years, and the second row is from 2015 to 2022. So it's almost 7 years. So it seems that we are progressing faster. And basically now we have the image of the Sagittarius A star. That is quite interesting. And by the way, also, the Nobel Prize in 2020 was given to Rainer Gengel and Andre Gage for the discovery of supermassive compact object at the center of our galaxy. So it was about the Sagittarius A star. So they basically showed how there is something very compact at the center of our galaxy, and we cannot see them, but what we can see is the trajectory around this supermassive object. So now moving on, when we image a black hole, when we want to see a black hole, what do we actually expect to see? I mean, what can we really see being at Earth? What can we really see? So first thing is that you remember about the accretion disk that I told. So this is the accretion disk of a black hole. So it's a hot, thin, rotating disk, and the material is slowly going, spiraling around the black hole. One thing here is that this guy is sitting at very strong gravitational field, so it will change the space-time around it, because that's what general relativity suggests us. So there are very different sort of gravitational effect that can be observed for this at this place. So what we can see is that the image of the disk underside. So we can see it's like a gravitational lensing thing. So we can actually see the lensed image of the accretion disk from the other side. Now we have the image of the disk's far side. So this far side that is in the other side, we can actually see it. It is twisted. That is also another GR effect. So what is actually there is just a black hole and a disk, but we see both sides of the disk at this plane. Now, another thing is that what we expect to see is a Doppler beaming. So as I told, like the material is going inside the black hole. So in one point, the material is moving towards us, and other point, the material is going away from us. So where the gas is flowing towards us, the accretion disk will look brighter. And when it is going away from us, it will look fainter. So this effect is called a Doppler beaming. So we are expected to see this. Then there is something called a photon ring. So basically, the event horizon of the black hole is inside this photon ring. Photon ring is this photons around this black hole. They travel very close to the event horizon in circular orbits. And what happens here is that either these photons can get absorbed into the black hole, or they can stay in the orbit, or they can escape to infinity. They can just deflect back depending upon what is the impact parameter. So whatever photon is coming back and going to infinity, which cannot like complete the orbit, they are actually coming to us. We are far away looking at these photon rings that are coming from here, from the black hole, that are not being absorbed by the black hole yet. So we can see these photon rings from infinity as an observer. Then what we actually see is a shadow of black hole. So black hole shadow means this point where we actually don't see anything. The black hole shadow term is used everywhere, but actually what you see is not a shadow but a selfhood. Means there is something dark in a very bright background. So that is what we are going to observe. We cannot see a black hole directly, but what we can see is how the matter is flowing around the black hole, and that can give us information about the black hole, how what is there inside it, right? So if we want to image such a thing, what do we really need? Like how difficult it can be. Let's try to understand that. So first of all, it is like you are on Earth and you are trying to click a picture of an orange which is in the moon. So it is that difficult to take a picture of black hole. So basically, these supermassive black holes are like far away, right? So and they are very small. Okay, it's something like the sun is very big, but it appears the same size as the moon because it is far away. So something similar. And the first thing that is needed is high angular resolution. So this is the formula for angular resolution. So R is lambda by D. Lambda is the wavelength and D is the length of the telescope, size of the telescope. So if we want to see a smaller object, then definitely we have to increase the size of the telescope. The smaller the object we want to see, the bigger the telescope we need. So to see such a small object, we really need a very big telescope. And for M87, the image we see is 22 microarc second, and for Sagittarius A star, it is 53 microarc second. So this is one thing that is really needed, that is high angular resolution. Now, the second thing is that high sensitivity. So these are basically radio waves, and we are trying to detect them. And they are far away, they are coming from far away. So what we are detecting through the antenna here are very weak signal. So for that we need high sensitivity to be able to capture these weak signals, right? Then we need modeling and simulation. Why is that? Because whatever we are getting, we don't know what it is. Like, we should have some reference to understand whatever we are getting in the observation, because in the observation, it doesn't know any physics, what is happening. It will just show what it sees. But to understand it, we have to do some modeling and simulation. So basically, there are simulations around black holes, and they are called the GR-MHD simulations. GR stands for general relativity, and MHD stands for magnetohydrodynamics. So they, in this simulation, what they do is that they study how the fluid is actually behaving near the vicinity of strong gravity. So, they use a lot of computation power, supercomputers, to do this kind of simulations. Now, all these criteria that I mentioned in the above two are fulfilled by a team of telescopes called Event Horizon Telescope. So this Event Horizon Telescope is not a single telescope, but there are a number of telescopes that are spread all across the globe. And what they try to do is that they try to look at the object from all these telescopes all together. So what we see, what is there in the sky, and we are collecting light from these different telescopes, and the Earth is rotating, and using the rotation of the Earth, these telescopes are able to cover more area in the sky. So this is actually interferometry. So what happens is that, so basically they place telescopes in different places of the Earth, and they are trying to make a virtual Earth-sized telescope. So basically, imagine that if there are telescopes all over the world, like all over the Earth, then we will be able to see the image properly. Like, we will collect all the lights that are coming from the image to us. But as I showed here, we have only specific points. So we can only get partial information about what is there in the sky. So this is the telescope, different telescope looking at an object. And now these telescopes are not everywhere in the Earth, so they collect only partial information about the image. It is something like, suppose, let's say you are trying to play a song in a piano or keyboard, whatever, but there, I will take few keys out. So you play the song, but there are few missing notes, right? So then still, like, how one can reconstruct the whole song from these missing notes, that is what is happening here. Now we have the measurements, and we have very partial information about the source. Now the question is that what the source look like. So here there are infinite number of possibilities. Like this can look like anything. I can fit any data to these lines. These are the measurements from the Event Horizon Telescope, and I can fit any data here. The question is there are infinite number of possibilities, then what do we really do here? So it's true that there are possibilities, but some are very unlikely, some are more likely, and some are very likely, right? So what do the scientists really do? So the Event Horizon team members, what they do is that they have very sophisticated, complicated image algorithm that they use to reconstruct this image. So how they do it is basically they have a library of simulations that I already talked about, like they simulate in computers how it should look like. In the computer, when they simulate, they have a reference frame, and through this reference, they try to understand what the information we are getting, how we can reconstruct a black hole image from there. It might like seem simple, but it's really not simple. And from this phase to this phase, it takes like years, like a lot of data, lot of image analysis is done, and there are a lot of complicated science. And thanks to the best scientists of EHT teams, they are able to reconstruct this image. So one interesting thing is that when they reconstruct this image, so basically they divide them in groups, and these groups cannot talk to each other, and they will come up with their own images, and then they should not be in contact, and then they see like how it should be, and that's how they really came to this black hole image. So as I said, the black hole image needs a simulation library to understand the black hole image. So to understand what is going on, what the event horizon is going to observe, so we need simulations, and there can be different parameters, and we change the parameters, and we can do the simulation around the black hole. So all of these simulations are computerized simulation done in a supercomputer these are simulation around black holes. Now that we have something to compare with, what they actually do with the imaging is that they produce a lot of images, like all the possible varieties that are consistent with these simulation models. And from these images, they do some sort of averaging of these images. Let's look at this video, how they do it. So these are different images that they reconstructed from the observation. This is for Sagittarius A star, and this is for M87. Then they cluster this image and take the average from these images. So they have, these can look like this. Then they take the average that is the most accurate, and that's how we get the image of Sagittarius A star and M87. Now, let's pause here for a moment. I told how they took the image, and we have the image now. Why do we do it at all? Like, I mean, why one should try to understand GR at all? Because GR is Einstein's general relativity is very famous theory, and it can actually be tested in different areas. Like if there is an atomic clock in the center of the Earth, then it ticks slower when it is away from the center. So there are effects of GR that can be really understood. And then there is this Mercury's orbit that is slightly different, and the effect is due to GR. By the way, every time you use a GPS, actually you are checking GR. That is kind of interesting, because so if you can see that GR is everywhere, that that has implications in our real life, it will be interesting to see whether this theory is really correct and how to know it, because black hole is such a place where the GR effects is extreme. So if they can confirm through observations that actually the general relativistic effect given by Einstein is true, then they should get the image as they expect from the theory. And that's actually what they get. But coming back to the image, okay, this image, like images do look like Bada to me, and like maybe to many of you, it looks like a donut or Bada or whatever. So what do we really know from these images? Like there are a lot of things going on in news and everything, but let me just summarize very briefly what I understood from all these images. So first thing is that I already mentioned that we will see one side will be brighter and one side will be fainter, and that is due to the Doppler beaming, because when the material is flowing towards us, it's bright, and when it is going away, it's faint. Okay. Then what we see in the sky is for M87, a ring of 40 microarc second, and for Sagittarius A star, a ring of 100 microarc second, right? Now, one might ask the question, why there is asymmetric ring? So if you remember the image of the black hole that I was showing, what we expect from the image, so there is some sort of ring that we expect, but why it will be asymmetric at all? It could be a symmetric ring because there is accretion disk. But the answer is somewhere here, where we have the camera. So the black holes are there, and the point that matters here is from which angle we are looking at them. So for the M87, we are looking at the M87, and this galaxy, this black hole is face on. So if it is edge on, we will expect something else, but it is face on. And another thing is that it is at 17 degree inclination. So if it is not inclined, then we will not see this asymmetric ring. But as it is inclined at an angle from us, we see this asymmetry in the structure. In the same way, when we look at the galactic center, so we are here, and the Sagittarius A star, it's in the galactic center. So we look at the galactic center, and then we find that it is also, we are also seeing it actually face on. We will expect that it should be edge on, but that's not true. It's actually 30 degree incline, and this is actually one of the new results that people got from this new image of Sagittarius A star. So now we know that the asymmetry of the rings in the black hole images come from the fact that from which angle we are looking at the black hole. Now, another question that you might ask, that why we see unequal number of bright spots. So yeah, there is here a structure like one bright spot, and here there are 3 of them, right? So what actually happens here? Let's try to understand this. So one thing is that M87 and Sagittarius A star are 2 completely different black holes. So Sagittarius A star is at the galactic center, and it's not very active. But M87 has this jet launching out of this elliptical galaxy, and it's very big, really bigger in compared to Sagittarius A star. So basically, in M87, inside the photon ring, we can fit the whole solar system in M87, and the Sagittarius A star, the whole structure is just the diameter of Mercury. So you can imagine the difference in their size, right? But in the screen, they appear almost similar size, because this is the one at the galactic center is close to us, and the one that is bigger in size but far away from us is away from us. So they are approximately same size in the observer screen, but we cannot ignore the fact that one is really big, almost around 1,500 times bigger than this black hole, right? So by the way, this M87 has a mass of 6 into 10 to the power 9 solar mass, and Sagittarius A star is around 4 times 10 to the power 6 solar mass, right? So why did I mention it at all? So you remember the like why there are uneven number of bright spots. That's what we were discussing. So let's imagine that I told that, okay, when we picture the black hole, we are not actually seeing the black hole, but we are seeing the material around the black hole that is glowing. So M87 is big, and the material is orbiting around it at close to the speed of light, but this is really big. So to complete one rotation, the light takes few days for M87. At the same time, Sagittarius A star is just here, and it's very tiny, I mean, compared to M87. So by the time light just crosses here, it can just take it can just make like a few times, few rotations around the Sagittarius A star. So why it's important? Why did I talk about it at all? So the thing is that when the EHT, Event Horizon Telescope, is looking at the black hole, it's basically taking its picture for few hours, right? So it takes the picture for 3-4 days, but every day it looks at the source for like 6 to 7 hours. Now M87, the material around it doesn't change so much for the observer, because it's really big and the material takes time to complete the orbit. So what we get from the flux we get from M87, it's almost constant. But for Sagittarius A star, it is variable, because the material is orbiting faster. So it's like you are trying to take a picture of a child running in a dark room. So you are just trying to take the picture. It was the same analogy for Sagittarius A star. The light is flowing faster around it, and we are trying to image it. Like we cannot we take few snapshots, but for each time the gas is in a different position and it's constantly moving. And if you look back at the image, as I told you, so this is some sort of average of the images that they got in the 3 days. So every time they take a snapshot, the ball is at somewhere else, then it again moves, then it again moves. So basically, it's like you can imagine that how it will look if you wait for some time. So this will look like 3 points then. So another interesting thing is that in 2019, what they were actually expecting was to get the image of Sagittarius A star. So the news was that we are going to get the image of Sagittarius A star, the black hole at the center of our galaxy, because it's closer. We can image it in an easier way. But this was really a problem to image a source which was really varying a lot, whereas it was easier to image M87. So these are some interesting things about the black hole image that you can understand from it. And yes, so these images are consistent with Einstein's general relativity. So the photon ring that are expected, that is around 2.5 times the event horizon, it actually matches with the theoretical prediction. So till now we know that Einstein's theory of general relativity is correct. So I already showed this. So before I end my talk, I thought to tell a little bit about my research. Luckily, I also I had a chance to work with one of the collaborators of this Event Horizon team, Maciek Wilgas, and Professor Lodek Luzniak is my supervisor. So what we are trying to do is basically I do computer simulation as well. If you remember the simulations I showed before in the slides, I do something similar. So these are called GRMHD simulation. So basically they solve general relativistic equation in a code, and we see how the material is behaving around a black hole. So what different I am trying is that, so basically we know that from the image that, okay, there is a thing that behaves like black hole, but can it be a black hole? Like, how sure we can be that it's actually a black hole? Because there are other theories of gravity that predicts the presence of wormhole or a naked singularity. A black hole without a event horizon is called a naked singularity. So basically there are other exotic astrophysical bodies that are present in the universe in different theories of gravity, of course. And what we are trying to see is that we are going to set identical accretion flow setup, and the thing I am doing is that I am changing the background around it. That means that when I have a core black hole means a black hole with a spin, no charge, and just a black hole with spin. The astrophysical black holes are usually core black hole. So we have core black hole, then we have a set of equation that satisfies like its metric. So basically we change this equation for when we have a different compact object, I mean a different exotic object like a naked singularity, then there are different sets of equation for this object, and we sort of change this surrounding of the object, and we want to see for identical accretion flow, the material is still the same around the around these objects, and we are going to see like is it something different? If such an object is producing image, will that look similar to what EHD is giving us, or it is going to be something different? That is something I am still studying. It's a work in progress. So here I just saw a screenshot from my simulation. So let me just explain very briefly. So here what you see is a black hole, and this is a cross section. So there is a disk around black hole, but you are looking at the disk like this. The disk is now puffed off. It's not like a thin disk, but it's like a little bit puffed off. So I am studying how the material is going inside. This is actually a Schwarzschild black hole, means it's a core black hole, but a special case of core black hole when the black hole is not spinning. So this is the snapshot from the simulation. And yes, so it is really interesting how we are getting the images of black hole these days. And imagine that there are going to be new telescopes adding to the EHD telescope. So basically, when we have more points, we get a better clarity. So it is expected that we cannot imagine what we can expect in the future. So that is something really intriguing. And thank you for listening to me for so long. And I will be really glad to answer any questions that you have. Maybe I missed some points, maybe I was going too fast, but you can always ask me question. And I have given some references for the paper that came for Sagittarius A star. It came very recently, so I just gave references to that those papers. So thank you. And if there are any questions, I will be happy to answer them.
Ruchi, first of all, thanks for this lovely talk. It was really interesting. Maybe if you can stop sharing, we can see more of you.
Yes, thank you.
Yeah. So I have a couple of questions, if you don't mind.
Yeah, sure.
Let me start off. The first thing is, of course, it's more of a trivial one, but just for the clarity of many people who are new to astro, Sagittarius A star is in the center of the Milky Way, and we are a part of the Milky Way.
Yes.
So
yes.
What do you mean by 17 degrees inclination? Because how do you have a 17 degree with respect to yourself?
We are a part of in Milky Way, that is true, but it's like not like a thin disk, right? So there is a plane, but still there is an inclination, like it's not exactly here, but somewhere down. And this is something that is known like recently from the image itself. Before, people were expecting that there should not be any inclination and we should just see it correctly, but that is a new result actually.
Okay. That's interesting. That's really interesting. And regarding your own work, my question is, what simulations exactly do you do? Is it a finite element kind or what?
GRMHT simulation. So GRMHT stands for General Relativistic Magnetohydrodynamics. So basically, we solve the magnetohydrodynamic equation in GR. So the code solves it. It's complicated. So we change different set of we can change the metric inside the code. Different.
No, my question is that I understand. Those are the physics equations.
Yes.
But what is the numerical method that you use to solve? Like, is it a finite element or is it?
Yeah, it's a mixture of a lot of things, like, because it's really complicated. It's not a code of few lines, but it's like really complex mess of codes. And there are, somewhere there are finite element methods and somewhere some other methods. And
so these are codes that are available to you?
Yes, so some of them are publicly available. Actually, the one I am using now is also publicly available in GitHub, but there are very few people involved. They are actually using it because they are very complicated.
I understand that. Yeah. Thanks, Ruchi. That was a lovely talk.
Okay, thank you. Are there any more questions?
Yeah, I would actually, yes, Alan, go ahead. Unmute, show yourself up on camera if you want.
Yeah, first of all, it was a really nice talk. I really enjoyed it. So, so the question I had is that while clustering to form the final image, like what are the parameters considered? Like, there should be some conditions, right? So is it dependent on the non-theoretical GR or
basically there are also other observations from these sources. So we can see these sources in other wavelengths. So these are, we have some idea about the diameter we are expecting and about the shape and things like that. So these are some constraints that they use while they are clustering. They just omit those images which doesn't fall into this category.
Okay, so like when you're simulating, like, do you find that more likely images, like not the very likely ones, but the ones that are more likely, do you find them interesting because like the computer simulations are showing that it is likely to have this kind of
Yes, of course, it's really interesting. So what we do in a simulation, we put the equations that we know and we let the computer solve it. Then we see how it looks. And the observation doesn't know anything about the simulation. What we are doing, they don't know. They see something in the screen. And when these are similar, then it's really interesting.
Okay. Thank you.
Thank you.
Any more questions? I think you can take this opportunity to ask Ruchi not just about her talk, but any other queries you have as your senior. She's a very friendly person, that much I can tell you.
Or if you don't want to ask me now, you can ask me offline as well.
Don't give them that option, Ruchi. Please let them.
Okay, then ask now.
Hello, ma'am.
Yeah.
I have one doubt.
Yeah, go ahead.
I have one doubt. Black holes.
Adigan, yeah. Go ahead, Adigan.
I read in one article, black holes is continuously emitting Hawking radiations. Is there any possibilities to find them using the Hawking radiations?
No. So the Hawking radiation is basically a theory, and even if they cannot be detected, like at least now they cannot be detected from Earth. So it is complicated to really look for these Hawking radiations from here. So yeah.
Okay.
Yeah, Ruchi, there is a question on YouTube from Devika, who just completed her project in Astro with
yes. So I see the question. So
I put it on the chat. It says, thank you for the excellent talk. Would Kerr black holes and Schwarzschild black holes give different kinds of accretion disks? Can you throw some light on the on frame dragging?
Yes, so Kerr black hole is basically like the Schwarzschild black hole is a special case of Kerr black hole. So when you do the simulation, like it will depend on the spin of the black hole. Like, okay, so in the Kerr black hole, the black hole has a spin. So the how fast you are rotating the black hole, that will affect the accretion disk. Like I have not simulated this kind of comparing these two black holes, but I think there are some papers that you can find, of course, where they actually do compare the simulation of accretion disk from Kerr black hole and Schwarzschild black hole. But yeah.
And she has a follow-up question. It says, why cannot we see the jet in M87 star black hole radio image?
Okay. So it's a very good question, but the thing is that we actually, there is a lot of debate going on. We are not very sure if there is some hint about the jet coming from the M87. So it's actually not yet clear in the community that what we see, it's nothing to do with the jet. So even there are some papers that speculates that what we are seeing actually the surface of the jet, not the black hole. But it's not very clear now, and there is a lot of debates going on about it. Like still there are a lot of papers coming. So yeah.
I hope that satisfies Devika and her questions. Anybody else? Any other questions also regarding where to apply for PhD, what to do? Okay, back to Nirupama or Asmita, whoever is taking care. Ruchi, thanks for that lovely talk.
Okay, thank you so much.
As we reached our today's discussion in time, it's time for us to thank Ms. Ruchi Mishra, who gave her precious time and a wonderful description of black hole, which always ignites fascination and curiosity in the minds of physics. I'm very much grateful and thank Dr. Madhurima ma'am who conducted this intellectual event. And to everyone present here, thank you for this event, for making this event a successful one. Thank you.
Thank you,
Okay.
one and all.